In this chapter, we will be studying applications of derivatives. In this lesson, we will once again be looking at examples of related rate problems.
Okay, hi everybody. Let's do some more related rates. So the total resistance, R, in a circuit where two resistors, R1 and R2, are connected in parallel is given by this expression right here. So there's my R and there's my two resistors. When the circuit is turned on, the resistance at R1 increases at 0.6 ohms per second and R2 increases at 0.3 ohms per second. Okay, so what do we know right now? Well, we know that dR1 by dt is going to be 0.6 ohms per second, and we know that dR2 by dt is going to equal 0.3 ohms per second. Now, let's just make sure, yeah, they're both increasing. Okay, I just want to make sure I didn't miss a negative in there somewhere. Okay, so how fast is the total resistance changing? So we are looking for dR by dt, don't know what that is, and we're given that R1 at some point here is going to be 80 ohms and R2 110 ohms. Now that's likely going to come into play later on. I'm probably going to have to use that to figure out what R is, I suspect, at some point here. Okay, well, what we need is an equation that relates all three of those, and we've got it. We know 1 over R is going to equal 1 over R1 plus 1 over R2. Now, there are a few things that we could do here. We could combine those all together. We could combine these two, reciprocate. We could do a bunch of different things here. It's probably just as easy, though, to do this. R to the negative 1 is equal to R1 to the negative 1 plus R2 to the negative 1, and then take the derivative just the way it sits right here. Although, I freely admit, you could do a few different things here. But now, if I take the derivative, this is going to be negative R to the negative 2 dr by dt, and I'm looking for dr by dt, so that's a good thing that that pops out here. This is going to be negative R1 to the negative 2 dr1 by dt, and I know both of those values right there, minus R2 to the negative 2 dr2 by dt. And again, I know both of those. So actually, I've got a lot here. Now, I'm going to divide, I'm going to divide by r to the negative 2. Actually, I'm going to multiply by r squared here. Now, but I am going to divide out the negatives here. So dr by dt, when all said and done, this is going to drop down to the denominator. This expression here, this factor is going to drop down to the denominator because of those negative exponents. Okay, and I'm going to multiply through by r. Okay, so essentially I'm going to multiply through, if you want to think about this, so I'm going to multiply through by negative r squared. Okay, let's go cancel on the right-hand side, and I'll be left with r squared over r1 squared dr1 by dt plus r squared over r2 squared dr2 by dt. Awesome. Now I've got almost everything I need, except I don't know what r is. But that's okay. That's why they gave us this little bit of information right here. So we know that 1 over r is going to equal 1 over r1, 80, plus 1 over 110. Oh, why did I put 81 there? That's so weird. Okay, 1 over 80 plus 1 over 110. Now, these right here, okay, I probably should just combine those together. Now, the lowest, all right, sorry about that, I gotta comment this again here. So the common denominator between 80 and 110 here, I think just 880, probably the easiest thing to do there. So what we do here is we multiplied 80. That's just going to be 11, and that's just going to be plus 8. And so altogether we are going to get 19 over 880. Now I'm just going to double check that with my calculator here, just because I don't want this to be wrong. And yeah, that is correct there. So now this, remember, is 1 over r. So to get r, we simply have to reciprocate that, and we'll get 880 over 19 ohms. That's going to be my r here. So now I can come up to my expression. Okay, we already know that R is going to be 880 over 19. So 880, over 19, this will be squared, over R1, and we know that R1 is 80. So I can already see that there's going to be some canceling here. And then this is going to be 0.6, okay, dr1 by dt. And this is going to be, again, 880 over 19 squared, whoops, over R2 squared. R2 is 110 squared, and dr2 by dt was going to be 0.3. Okay, now because all of that is, because I've got the two decimals there, I suspect that the final answer can be written in decimal form, and there won't be a problem with that. So on my calculator, I will just enter that expression in. Okay, and I get that dr by dt is going to be 0.25 ohms per second when you evaluate all of that together. Okay, so that's how fast the total resistance is changing. All right, in this video we read that the light on the top of a lighthouse situated 3 kilometers off a straight shoreline. Okay, so let's just figure out what this looks like. So, lighthouse, 3 kilometers off of a straight shoreline, rotates at 6 revolutions per minute. Now, I've often had students struggle with this, what is meant by that, 6 revolutions per minute. So that means that this thing is going around, okay, 6 times in a minute. Now let's just think about that. If we think about the angular motion here, that means if we use theta to determine the angle that this thing is rotated at here, d theta by dt is going to be 6 2 pi's, okay, per minute. Or in other words, this is going to be, it's going to cycle through 12 pi radians per minute. That's what's meant when we say 6 revolutions per minute. We're talking about the angular velocity of this thing. So now, straight to the shore, okay, looks like that. And then the question is, how fast does the beam sweep across the shore when the angle between the beam and the shore is 40 degrees? In other words, this thing's going around 12 pi radians per minute here. It's going to leave a dot on the shore, and we're wondering how fast that dot is moving. Let's call this variable here x, the distance that that point of light is from straight across. Now that gives us a bit of a reference there. So what this question is asking for is, what is dx by dt? Dx by dt. Don't know what that is. Now we're going to throw an angle on here, except we got to make sure that we do this carefully, because the angle that we're given here is the angle between the beam and the shore. Well, that's this angle right here. But d theta by dt is the angle that it's rotating at. That's actually going to be that angle right there. So now it's not hard to figure out what that is. If this is 40, well, then we know that at that specific moment that we're interested in, this is going to be 50 degrees. Okay, however, something to be aware of, these word problems, anytime we do this in calculus, the word problems should be in radians here, okay? So let's just convert 50 degrees into radians. That's going to be 50 degrees. We'll multiply by pi over 180. And that makes actually for a relatively simple conversion here, because we can cancel the factors of 10 there, and that just becomes 5 pi over 18. So that's the angle that we're interested in, okay? So at the instant, that theta up there becomes 5 pi over 18. Okay. We're interested in how fast that particular little dot of light is sliding across the shore. Okay, well, let's just take a look at the scenario here. So this theta here is changing, okay, and it's causing this to change right here, x. But this part right here, this side of this triangle, this right triangle, this is never going to change. So that's my adjacent, and I'm looking for how fast the opposite is changing. Well, that's the tangent ratio. I'm not given any information about the hypotenuse, and I'm not asked for any information about the hypotenuse. So I can actually use the tangent ratio here. Okay? So the tangent of theta, in this case, will be x over the 3 kilometers. Okay, Well, now let's figure this out. Okay? When we take the derivative of this, the derivative of tangent is going to be secant squared theta d theta by dt. Okay, that's important because we are looking for, we're given d theta by dt. Now we're looking for dx by dt. And on the right-hand side, we're going to get 1 over 3 dx by dt. So there we go. We got the dx by dt out of there. Now, we're going to bring the 3 over, so this will be 3 secant squared of theta d theta by dt is equal to dx by dt. Wonderful. Well, now we have everything we need. Okay, we know that we got that 3 there, and we know that's going to be in the numerator. I'm just going to convert that secant into a cosine. So this will be 3 over the cosine squared of theta d theta by dt. That'll just make it easier to enter into the calculator here in just a second. Sometimes, based on the information that I'm given, sometimes instead of evaluating what the cosine is by using the calculator, I can actually use the triangle in some information here. But in this particular case here, I actually have that angle as 5 pi over 18. Now, in this case, I didn't actually need to put that into radians, okay, because I'm going to use the cosine. And the cosine is going to convert that into the ratio. Now, whether I'm in degrees or radians, I'm going to get the same ratio for that same angle. But it's a good idea to be in radians when you're doing trigonometry and calculus. It's just always a good idea. So this right here is going to be 3 over the cosine squared of 5 pi over 18 multiplied by 12 pi per minute. Because remember, it's radians, and radians are a dimensionless measure, so 12 pi per minute here. So on my calculator, whoops, first of all, I've got to make sure I'm in radian mode. That would be embarrassing. So 3 divided by the cosine of 5 pi divided by 18, and we're going to square the cosine, and then we're going to multiply by 12 pi. And so we get that this is going to be 273.7 kilometers per minute. Okay, that is my dx by dt. Now again, I know that that's kilometers here because actually the only unit that I had in here was a kilometers. The only length unit was this one right here. Okay, that 3 was a kilometer there. So those are the units that survive. 273.7 kilometers per minute. Okay, so in this question we read that a 5-meter extension ladder leans against a large wall. Now, the fact that they call that an extension ladder suggests something to me. Okay, so an extension ladder can change in length. So we're probably going to watch this ladder change length. The foot of the ladder is anchored 2 meters from the wall. Okay, so here we go. So what do we know about this situation right now? Well, we've got a wall here, and we've got a 5-meter extension ladder, and it is anchored 2 meters from the wall. Okay. When the person responsible realizes that it was put there upside down, there it is. So yeah, the ladder is going to change length here. So as the ladder collapses, the top of the ladder slides down the wall, and the length of the ladder decreases at 1 meter per second. Okay, let's call the different lengths here, the different sides of the triangle here, x, y, and z respectively here. So what we've just been told is that the ladder is changing lengths. So dz by dt, and that's going to be -1 meter per second. Negative because it's getting smaller here. Okay, how fast is the angle between the ladder and the ground changing? Okay, so let's call that theta. So the question that we're asking for here is, what is d theta by dt? How fast is that angle changing? And we're told when the angle is 30 degrees. Okay, now once again, I know I said this before here, but with word problems in calculus, we typically want to be in radians. I'm going to stick with radians there. So I'm going to call that, instead of 30 degrees, pi over 6. That might not be an issue at all. It might not matter at all that I'm in radians or degrees. However, it's just a good rule of thumb. Good to be in radians there. Okay, so let's just take a quick look at this. Here's my theta. That's what's important here. Now, my y is changing, it's collapsing, but I haven't been given any information about that, and I'm not asked about it. Z is changing, and I've been given some information about that. It's -1 meters per second. And X isn't. Well, I like the fact that X isn't. I mean, I really like that. Because when I build my equation, I can throw that in as a value immediately. So I'm thinking that what I want to do here is I want to relate these two variables together because this one doesn't change, and I know how this one's changing to theta here. And so the trig function that relates those three is going to be cosine. So the cosine of theta will be x over z. Now I'm not going to plug in 5 in for z because that's changing with time. Okay? It's not going to be the same value all the time here. In fact, 5 was just the initial length there. So now I will take my derivative. Oh, sorry, I'm not going to take my derivative quite yet. I'm going to plug in what I know first because I'm kind of lazy, and if I can throw a constant in there, I will. And my constant there is 2 for x. Now I'll take the derivative. The derivative of cosine is negative sine theta, and then the derivative of theta will be d theta by dt. That's what I want. Okay, I want d theta by dt. And then over here, this is going to end up being -2 over z squared dz by dt. Okay, now and again, if you're wondering where that all came from, all I did was I rewrote this as 2 multiplied by z to the -1. So brought down the negative and then subtracted 1 from the exponent. So there you go. Okay, I am looking for d theta by dt. So I'm going to divide both sides by sine of theta. So d theta by dt is going to equal, okay, well then now the negatives are going to cancel there. Okay. Is that right? Yeah. Okay. And so that is going to be 2 over z squared sine theta dz by dt. All right, now I'm going to start to plug things in. So I know that that theta here is going to be pi over 6 or 30 degrees. So again, it turns out that it didn't matter whether I was in radians or degrees or not. That's okay. Z I need to know, but I don't. Okay, I don't actually know Z at this point here. So I'm actually going to have to go down here and do a little bit more work to figure out what the value of Z is. Okay, if this is 2 and this is 30 degrees or pi over 6 here, what is Z here? Now, that's going to be cosine, again, relating those together here. So the cosine of 30 degrees is going to equal Z. Oops, shoot. Man, I did. That is totally a classic mistake here. This is going to be 2 over Z. Okay, but I know why students do that. I mean, a lot of students do that. They'll instinctively put the variable up top, even if it's supposed to be in the denominator, simply because it's easier to work with. So now I know that the cosine of 30 degrees is going to be √3 over 2 is going to equal 2 over Z. So Z is going to be 4 over √3. Now, maybe you have to rationalize, maybe you don't. But if you do, then Z becomes 4 √3 over 3. Okay, now I'm not going to worry about that. I'm going to leave that as 4 over √3 because I'm not as insistent that people rationalize. Maybe I should be, but I'm not. Okay, and besides that, when I go back up into my expression here, when I plug stuff in, this is going to be 2 over 4 over √3. This is going to be squared, and that's really why I didn't really care that much, because when I square that √3, I'm going to get rid of that radical anyway. Sine of 30 degrees, or pi over 6, and then we're going to multiply by dz by dt, which we know is -1. And actually, I'm glad that popped out here, because I know that that angle is going to change, and it's going to get smaller. Okay, as that ladder slides down like this, that theta is going to become a smaller value, so I need its change in to be negative. The 2 negative here canceled, so I needed there to be another negative to pop out, and there it is. Okay, so let's put this all together. This is going to be -2 over. This will be 16 over 3, and sine of pi over 6, sine of 30 degrees is 1/2. Okay, so down here in the denominator, that's going to be -2 over 8/3. I'm going to multiply by the reciprocal, so that 3 is going to go into the numerator, but I've got a 2 over an 8, so it's going to be -3 over 4. Now, with what units? Well, I was in radians. Okay, I was in radians. So it's going to be negative 3 over 4 radians, okay, per second. Now, regardless of whether I was in degrees over here, you need to know that that is a radian when it spits out at the end here. Which is, again, a good idea to be in radians, to understand that word problems in calculus are going to be in radians. When you get that d theta by dt, it's just going to pop out in radians. Okay, so negative 3 over 4 radians per second. That's how fast that angle is going to be changing. Okay, now in this question we read that two sides of a triangle measure 10 and 12 centimeters. The angle between them increases at pi over 12 per second. How fast is the area increasing when the angle between them is pi over 2? Okay, now, classic mistake that gets made here. Okay, I often see people do this. They'll draw the triangle like this. They go 10 and 12. The angle between them, okay, so we got this theta between them. It's getting larger. So we want to know what the area is. The problem with this diagram here is that it doesn't lead nicely to a solution because I'm asking for the area and I don't know the base. I also don't know the height. Okay, and there's really no clean way of doing it because this isn't an isosceles triangle. Okay, or at least at this point with these two sides here, I mean it's not likely to be like that. So I can't just divide that in two and expect to get the answer here. It doesn't work like this. This leads to a frustrating situation here. So don't do that. Don't draw it like that. Do yourself a favor. Draw it like this. So let's pick one of those sides. Let's make that the 10. And here's 12. And so now connect the two endpoints there. And let's make this here theta. So now in this scenario right here, I know that d theta by dt, okay, is increasing at pi over 12 radians per second. And now I'm interested in how the area is increasing. So dA by dt. Now I don't know what that is. Okay, that's okay. That's okay. I do at least know the base of the triangle. Now if I want to get the height here, and as theta changes, I know h is going to change. So what I want to do here is I want to come up with some sort of an expression for height in terms of theta because d theta by dt is what I'm given. I know that I need h to come up with the area of the triangle, but this is the rate that I've got. So I want to connect those two right here, and my base is just going to be 10. It's a constant. I love that. Okay, so let's take a look at this. Well, 10 is not going to help me because 10 is the length of the entire base there, and that's in this right angle triangle, that's just not applicable. So I've got theta here, h is my opposite, 12 is the hypotenuse, so that is going to be sine. The sine of theta is going to be h over 12. Wonderful. Okay, so now I know that h is going to be 12 sine of theta. Perfect. Because now what I can do is I know that my area is going to be 1/2 base times height. But I know that the base is 10 because of the way I drew the triangle. I did myself a favor there. And now I know that the height is going to be 12 sine of theta. Wonderful. Now I'm going to simplify. So that's going to be 60 sine theta. And not only does that simplify beautifully, but the derivative is going to be beautiful as well here. So the derivative of a with respect to time is going to be 60 cosine of theta d theta by dt. Wonderful. Absolutely wonderful here. So now, how fast is the area increasing when the angle between them is pi over 2? Okay, well, I've actually got everything I need. I know what d theta by dt is, and I know what theta is. So this is going to be 60 cosine of pi over 2, and then that's going to be pi over 12 per second here. All right, Well, cosine of pi over 2 is 0. Well, that means the whole thing goes to 0. Well, does that make any sense? This is like 0 centimeters squared per second. Now, that's not a very satisfying answer, but actually it does make sense. Okay, so let's just take a quick look at what's going on here. Here's my scenario. Here's my base. And so here's my 12 here, making a triangle here. Now, we're going to let this angle increase here. So, goes up to pi over 2, and then it goes out like this. So here's my 10, and here's my 12, here's my 12, here's my 12. Now notice that when the angle here is less than 90, when theta is less than 90, the triangle that I form here, its area as I rotate this out is increasing. It increases, it increases, and increases until I get to that angle pi over 2 between them. Then all of a sudden my area becomes a maximum. From this point on, okay, as that angle becomes obtuse, the area of that triangle gets smaller and smaller and smaller. Okay, so basically, it's when this thing is right up vertical here that I've got the largest height. At any other angle here, the height gets smaller and smaller, so that the area gets down here. So actually, that makes perfect sense, because that's the moment that the area changes from increasing to decreasing. It's like when you throw an object in the air, it hits its peak and drops back down again. It goes up, 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 stops just for a moment, and then drops back down. Well, we're asking for that exact moment where it transitions from increasing to decreasing. So yes, that actually makes perfect sense. All right, now in this question, the issue here isn't really the developing of the equation, because the equation's given to you. Okay, this is really just an example of a question where the function is a little bit different, requires a different sort of a derivative. So the decimal value n of a sound is given by n equals 10 common log of I divided by 10 to the 12, where I is the sound's intensity measured in watts per square meter. So if the intensity of a sound is increasing, so here we go, here's our rate. The intensity is increasing at 20 watts per meter squared per second. Okay, so what do we know here? Oops. What do we know? Well, we know di by dt. Okay, that's going to be 20 watts per meter squared per second. Okay, then the question is, how fast is the volume changing in decibels per second? So we're looking for dN by dt. Don't know what that is. When the sound is 70 decibels, so when n is equal to 70 decibels. Now, I suspect because I'm giving the n here at 70 decibels, we're probably going to have to find I at some point here. But I don't know. Until we get into the equation, I don't know. But the relation is given to us. I don't have to come up with that. So n is equal to 10 common log of I over 10 to the 12. Now, because this is a logarithm, we've actually got the ability to play with this a little bit before we take the derivative. Now, if I was to take the derivative of this right now, it really wouldn't cause me too much trouble here, quite honestly, because there's really not that much happening with the variable, and the variable in this case is I. So whether you wanted to dive right in or not, you would have no problem doing this problem. But I want to suggest to you that take advantage of the laws of logarithms when you can. And so that's what I'm going to do here. I'm going to make this n is equal to 10 times, I'm going to put brackets here, the log of I minus the log of 10 to the 12. Okay? So that division within a logarithm becomes subtraction between logarithms. And then I'm going to distribute that 10 through. So 10 common log of I minus 10 common log of 10 to the 12. Now, I didn't. Yeah. Don't know why I wrote that. I just got rid of that. Now, I already know, and I can see I can see it just as clear as everybody else here that this is going to be 12, this is going to be 120 here, but I'm going to leave it like that because right now what I end up doing is taking the derivative, dn by dt, and which is exactly what I'm looking for, by the way. I want dn by dt. I want to figure out what that is. That is going to equal, okay, the derivative of the natural log. So first of all, there's that coefficient 10. The derivative of the, sorry, not the natural log, the common log will be 1 over the argument, so 1 over I, and then this will be the natural log of the base, which is 10. Then because of the chain rule, we'll multiply by the derivative of what's inside, we'll multiply by di by dt. Now, this is a constant over here, its derivative is going to go to 0. So it's just going to go away here. So it didn't matter. I mean, I could have evaluated that, yes, but it was irrelevant because I was taking the derivative and it's just going to go away. So now I got to figure out what this is, and I've got almost all the information I need. I know di by dt, okay, that's 20. I can figure out this stuff on my calculator pretty easily. What I don't know is I, though. So I got to go back to our original relationship here and figure out what I is. So I know that n is equal to 10, okay, common log of I over 10 to the 12. And I know that this is supposed to be equal to 70 at the specific moment that I'm interested in. So 70 is equal to 10 log I over 10 to the 12. Divide both sides by the 10. 7 is equal to the common log of I over 10 to the 12. Now, in order to evaluate for the variable inside the argument of the logarithm, I need to get rid of the logarithm. Like all of these kinds of problems here, when you want to solve a logarithmic equation, the issue is to get rid of the logarithm. If you want to solve a trig equation, you've got to get rid of the particular trig function that's got the variable in it. So it's the same sort of thing all the time here. So I got to apply the inverse operation here. So this is a log base 10. So I've got to apply the inverse operation 10 to the power of. So this is going to be 10 to the power of 7 is equal to I over 10 to the 12. That's how we get rid of the logarithm. Now you're going to be, there's all sorts of ways of remembering how to do that, but really it's just the base raised to this value as an exponent. A logarithm is an exponent. So 10 to the 7 gets rid of the logarithm. Now multiply through by 10 to the 12. And when you multiply powers with the same bases, you simply add the exponents. This is going to become 10 to the 19 is equal to I. Okay? So now we've got a value for I. Now we can go back up into our expression here. And so this is going to become 10 over 10 to the 19, natural log of 10. And this is all going to be multiplied by 20. 20 watts per meter squared per second. Okay, now we got that huge number down there, so I expect this number is going to be pretty small when we put this all together. But with that natural log of 10 here, let's figure out what this is going to be. So 10 divided by 10 to the 19. There's a natural log of 10 in there. And then I'm going to multiply by 20. And we get this ridiculously small number here. This is 8.685 and so on and so forth times 10 to the negative 18. So what we've got here is really, just write this out, approximately 7 times 10 to the negative 18 decibels per second. All right. So it's increasing in sound, but not by a whole lot. There you go. Okay, now this question is really here just to tip of the hat to the other math course that we teach at the school where I teach here. This is a question that's commonly asked in the grade 12 year. So the pH of a solution is given by pH is equal to the negative log of H to the positive sign here, where that symbol right there is the hydrogen ion concentration of the solution. Now, if due to a titration, the pH of a solution decreases at a rate of 0.7 per minute. Okay, so what do we know here? Well, we know that the rate of change of the pH is going to be negative 0.7 per minute. Okay? So then the question is, how fast is the hydrogen ion concentration changing? Okay, so we want to know what that is. When the pH is equal to 5. Now I suspect, again, and I've given you information like this, that I'm probably going to have to figure out what the hydrogen ion concentration is at that particular moment before I can finish the question. Now, I don't know that for sure though, so let's dive right in. What's the relationship between the pH and the hydrogen ion concentration? Well, we know what it is. It's pH is equal to negative common log of the hydrogen ion concentration. So now if we just jump in and take the derivative dpH by dt, now I know what that is. It's going to be negative 0.7, so that's good. It's going to equal, okay, so when I take the derivative of a common log, that is going to be 1 over the argument. So there's the hydrogen ion concentration. So yep, I do need to go back and figure out what that is. This will be multiplied by the natural log of 10, that's the base, and then multiplied by the rate of change of the hydrogen ion concentration. Okay, that's because of the chain rule. Okay, well, I've got almost everything I need. It's just that one little thing there. I don't know what the hydrogen ion concentration is when the pH is 5. So let's plug that in. So 5 is equal to the negative log of the hydrogen ion concentration. Bring the negative over. And now, for me to solve the logarithmic equation here for the argument, I need to get rid of that logarithm. And I do it by applying the inverse operation. So because this is a log base 10, okay, the inverse is going to be a power with a base of 10. So this will be 10 to the negative 5 is equal to, and those will cancel, and I'll just be left with the hydrogen ion concentration. Now, in a lot of cases, when you evaluate that, that would not be an acceptable answer. In a lot of other contexts, that wouldn't be acceptable. You want to put that into scientific notation here. But for right now, I just needed that value because I'm going to take it and plug it back up into my expression here. So I'm not going to worry about putting that into scientific notation. So this will be negative 1 over 10 to the negative 5, natural log of 10, and then the dH plus by dt is going to be negative 0.7 per minute. Okay, so now let's evaluate that. That's going to be positive 0.7 divided by 10 to the exponent negative 5 multiplied by the natural log of 10. Ooh, and we get, what is that? We get per minute. Now, I forget the units for concentration. But this is reasonable because we're talking about really, really large numbers. And this is why we're using logarithms here. So this is probably going to be, what is that, 3.04 times 10 to the 1, 2, 3, 4. I don't even know what units they use for concentration. Something, was it moles? I'm probably going to guess here, moles per liter per minute as my rate. I'd be very shocked if I guessed that correctly. Anyway, I should have looked ahead on this problem before I started it with respect to that right there. Anyway, take it for what it is. There's the value. All right, so one final problem here. Air pressure, P, depends on altitude, Z, by the following function. So P is equal to P naught e to the negative mgz over kt, where P naught, m, g, k, and t are all considered constants. So how fast is the pressure changing? So what do we know here? We are looking for dp by dt. How fast is the pressure changing? At the instant, the altitude is 3 kilometers. So I don't know what that is. But we're looking for it where z is 3 kilometers. If the altitude decreases, so dz by dt is decreasing, okay, at a rate of 50 meters per second. So negative 50 meters per second. Okay. Well, our expression here is P is equal to P naught e to the negative mgz over kt. So I just needed an expression relating P and Z. So now I can just jump right in. So again, the purpose of this question is not about the building of the equation, but more about just a word problem application with a different form of function so that we can do a different kind of derivative here. So dp by dt is going to equal the derivative of this right here. But the only variable is z. Everything else is considered a constant. So this is going to be p, okay, p naught, e to the negative mgz over kt, because the derivative of an exponential function, well, okay, the derivative of the exponential function, because this is e to some exponent, is going to be itself multiplied by the derivative of the exponent, which in this case is going to be negative mg over kt, and then multiplied by dz by dt. Okay. So now we're just interested in how fast the pressure changes. So dp by dt at this particular value here. Well, there's really not much that we can do here other than plug in the values of the variable here. So this is going to be p naught e to the negative mg times 3 over kt, negative mg kt, and this will be multiplied by negative 50. Okay? So now let's just reorganize that a little bit. There's really not much going on here. The negatives are going to cancel, so this is going to be 50 mg p naught over kt. That's just me bringing, whoops, sorry, you can't even see that. Me just bringing the variables over, and then multiplied by e to the negative 3 mg over kt. And that's your dp by dt. Okay? Everything here is a constant. That is about as simple as it was going to get here. Now, the reason why we don't do much more than this is because in a lot of the other questions here, when you took the derivative, there was something that allowed like the independent variable to stay, or the dependent variable there to stay, so that you had to solve for it. But in this case, it just didn't happen. The derivative was much simpler, but it was an exponential function, so it was a little different than the ones that we've previously done. Okay, that might not be terribly satisfying because it doesn't look like it's simplified all that much, but it's good. All right, now really quickly before I completely leave here, yes, I just noticed the mistake. That was after the fact here. Bear in mind that 3 is in kilometers up in the question. Okay, it says 3 kilometers here. So this is actually, whoops. Because the 50 is in meters here, I need the units to be the same here. So this has got to be 3,000 meters. So that actually changes this expression a little bit here. This will be 50 mg over kt p naught e to the negative 3,000 mg over kt. Okay, sorry about that. That was completely unintentional, but there you go.